All right, you guys, today we are going to prove triangle congruence with HL, that's hypotenuse leg, ASA, angle side angle, and AAS, which is angle angle side. So just a reminder up above, a triangle is unique if only one triangle can be drawn from given information. So any other triangle with that same information would match that first triangle perfectly. They would be congruent. Okay, we've already learned about two. We've learned about two combinations that work. We've learned about side, 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 and side, angle, side. So today we're taking on the other three relationships. Okay, at the top, just a reminder that we do have two combinations that do not work. If we have angle, 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 right, it doesn't lock our triangle into a unique rigid position. If I only know the three angles, this triangle could be much bigger or much smaller. I could scale it up or shrink it down and preserve the angle measures. So angle, 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 we know it does not work. I usually just give a little X right here. Does not establish a unique triangle. So if I have two triangles with that same information, they are not necessarily congruent. Okay, side-side angle is the other one that does not work. Let me give a little X right here. So in my diagram, I'm showing you that I know two sides, but it's the non-included angle right here that's the other information that I know. So what ends up happening is right where B is, right in between the two known sides, that becomes a hinge. So a hinge right here and a hinge right here. So that this side right here where BC is, it's not locked into a rigid position. And this side here could swing into an alternate spot right here and make a very different looking triangle like you can see over here. So side-side angle doesn't work. We have two very different triangles that could emerge with that same information because again, we know the non-included angle, it has to be the included angle to make a rigid, unique triangle. All right, so the other three combinations that work. We know HL. So HL is hypotenuse leg. It's a special case of side-side angle, but only for right triangles. So if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So I'd have to know, for example, that O and Y are right angles. So these are right triangles. Hypotenuse to hypotenuse. Remember that the hypotenuse is the longest side of a right triangle. It's always opposite the largest angle measure, which is the right angle. So then I just have to link up one pair of legs. And it could be either pair. I'm going to mark it as this pair right here. So this would be hypotenuse leg, so a special case of side-side angle, but only for right triangles. Let me write that here. So SSA for right triangles. Okay, and if I want to write a congruent statement, let's say that I name the first triangle CNO. So C to N to O. Over here would be RAY. You always want to link up those corresponding parts in proper order. Okay, next one here we have angle, side, angle. Notice where the side is, right? It's tucked in between the two angles. So if we have two angles in the included side of a triangle, and they're congruent to two angles in the included side of another triangle, then the triangles are congruent. So what's crucial here is that word included. That is essential. So let's say that I tell you that angle E and C are congruent, and then P and Y are congruent. So those are my two pairs of corresponding angles that are congruent. If I need their included sides, it has to be the sides that are directly in between those two marked angles. So it has to be here and here, right? It has to be included it has to be in between the two known angles. So now if I write myself a statement, I can say that triangle PEA, so PEA will be congruent to YCH. Okay, and then lastly, angle side. So here the side is not included. So if two angles and the non-included side of a triangle are congruent to two angles and the non-included side of another triangle, then the triangles are congruent. So let me just underline that non-included part. All right, so here let's say that I tell you that angle C is congruent to S and angle A is congruent to R. So here's my two pairs of corresponding angles. So now I need a non-included pair of sides. So that means that I could link up these two sides here or these two sides here. They just can't be the sides in between the two angles. So I'm going to go ahead and give a tick mark here and here. But I had a choice here for what to link up to show you angle side. So now if I call the first one CHA, for example, so CHA, then I want to go SMR. Okay, so then I just wanted to show you a little bit more just with some tactiles before I go into example 1. So if I'm trying to show you HL, hypotenuse leg, so imagine that I know an angle is right. I know it's 90 degrees. Let me put that right there. All right, and I know that I have a side here that is 6 inches. Okay, let me take my ruler and show you just what the straight pathway would have to be for the other leg right here. Right, I don't know its value, but I know the pathway it would have to be on because it runs perpendicular with this leg right here. So then my hypotenuse, right, my longest side, only has one position to fall into. It has to fall in right here. There's no other place for it to go, right? So it creates a rigid, unique triangle if I know the right angle, I know one leg, and I know the hypotenuse. So let me just zoom out a smidge so you can see everything right there. So again, there's only one triangle that I could create with that information. Any other triangle with that same information would match this first one perfectly. All right, if I look at angle side angle. So here I know two angles and the included side. So here in my model, I'm giving you 8 inches for that known side. I have an angle that's 60 degrees and an angle that's 45 degrees. So if I use my rulers again, so let's say that I put in this pathway, right? So this pathway has to create that 60-degree angle, and this one right here has to create a 45-degree angle. Then I can see that it has to be a triangle where these two sides fall into these two positions. And if I overlay with some colors, right, I can show you, let's see, like this. Right here would be the triangle that I would be creating with that initial information of just one side that's included. It's in between the two known angles. So my triangle would have to look like this, right, with just that initial information. All right, if I do the same thing for angle side, so let's say that this is my starting point, right? I know that this angle is 75 degrees. This side is 8 inches. Okay, I don't know this side right here. I'm just going to hold its pathway with a ruler, just like that. Okay, and then I'm going to put in here another angle somewhere along that pathway. Let's see, I'll do it like this. Okay, so what I'm going to see then is if I have two angles and I have a side, then what's going to happen to create that pathway right there is I'd have to get a triangle that looks like this. Okay, so if I know two angles and a side, so here I have a 45-degree angle, I have a 75-degree angle, this angle would be locked into a position as well. So if these add to, let's see, 45 and 75, if those add to 120, then I'd have to have an angle right here that would be 60 degrees, and that would be locked into a specific position, and then these two pathways would be locked into a specific pathway as well. So angle, angle, side, really, since we know two angles and one side, we actually know the other angle too. We know the angle right here would have to be 60 degrees to then lock it into this specific unique position. All right, so I just wanted to bring home those relationships and show you why they create a rigid, unique triangle. All right, so next, going through example 1. So example 1 here, I'm giving you certain information, and I want to see if we can determine that the triangles are congruent by any of these 5 combinations that we've learned about. So side, 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 angle, side, hypotenuse leg, angle, side, angle, or angle, angle, side. And sometimes we have to fill in some extra information to make some connections. So I'm going to write that off to the side just so we have a sense of how we're connecting extra additional pieces of information. So first up, I'm saying, okay, these are my two triangles, and I'm looking at STO. So I'm looking at STO, which means I'm trying to see if it's congruent to SPO. So based on what's marked, I can see that if that's a right angle, this has to be a right angle as well, because they both have to add to 180. And then I have a common side right here, right? It's the same side for both triangles, so that's really the reflexive property of congruence. I'm going to always write it because this is important for when we start writing our proofs, right? I want to know, why can I link up SO to SO? Well, it's the same side for both, reflexive property. So then I can say that STO is congruent to SPO because I have two right triangles. I have a hypotenuse to hypotenuse, leg to leg. So my reason is HL. Okay, in my next one, here I have some parallels, so I'm going to use that same strategy. I have parallels here. Okay, and then I have a transversal then that is right here. So then I can link up my alternate interior angles here and here. So my reason would be the alternate interior angles theorem. And now I have a pair of sides and a pair of angles. I see that this is the same side for both triangles, so I'm going to give it a double tick mark. My reason would be the reflexive property of congruence again. We use it a lot in this unit, and we just use it to say we're linking up one side to itself. So it's a common side for both triangles. They just share that same side. All right, so we're seeing essentially that this parallelogram, right, I'm kind of foreshadowing where we're headed. So we're seeing that it splits into two congruent triangles, and it's congruent by a rotation. I can see that this triangle would rotate 180 into this spot. They're congruent because we have side, angle, side. It's the angle that is directly in between those two known sides. So SOW will sync up to WNS. And my reason would be side, angle, side. Okay. All right, next up. So here those arrows mean parallel again, so I'm just going to emphasize them. Okay, then if I'm trying to make a connection and I have these tick marks here and here, then I'd probably view this one as my transversal. But I could have used the other one as well. You'll see why I picked this one in just a moment. All right, so here I can connect these alternate interior angles right there. So T would be congruent to O. They are alternate interior angles. So I'd be citing that theorem to make that connection if I was writing this as a formal proof. So now I have one pair of sides, one pair of angles. So what other connection can I make? Well, I see vertical angles right here. So that would be the vertical angles theorem if I was writing this as a proof. All right, so now I have two angles and a side. That side is directly in between the two angles. So I have angle, side, angle. And if I call the first one PST, the second one would be PRO. If instead I had linked up these two angles, I could have had angle, angle, side. That would have been fine as well. Some of these have alternate pathways, so you have alternate ways of getting to your end result. All right, this next one here, we're looking at CEH, so I'm looking at this triangle and this triangle. I'm given this angle marked. It's a right angle. I see that box notation. So its vertical angle would also be a right angle, and right angles are congruent. So I'm just acknowledging that I'm citing the vertical angles theorem to make that connection. And then I really have enough, right? Because I do have side, angle, side. So even if it's a right angle, still a pair of angles that are congruent. So I can still say side, angle, side. So if I name it CEH, over here would be OER. And my reason would be side, angle, side. Okay, one other thing that you might notice is that it's not just these triangles that would be congruent. These triangles would be congruent as well, because they're all going to be right angles in this middle space right in here where those diagonals cross. So this is something, again, I'm just foreshadowing where we're headed eventually, where this is actually a figure that's a rhombus, and the diagonals bisect each other. They are also congruent right angles. And we see that we get these four congruent right triangles that result in the interior space. All right, next one, E. Here I'm given these angles are congruent, these sides are congruent. I'm trying to prove DCO. So DCO. So I want to link that to DSE. So what can I link up? Well, I got a lot of vertical angles here too. We saw that a lot. It's a common reason that we use to make connections. So I can see that those vertical angles are congruent. So this would be the vertical angles theorem. And when I named the first one DCO, the second one would be DSE. My reason is angle, angle, side. Okay. Next up. So next one here, we're looking at SDI as our triangle. So this one gets a little bit more complicated. So I'm looking at this triangle right here. That triangle. So I'm trying to link it up then to this triangle over here. So I think a good strategy whenever you have overlapping parts like this is to draw them out as two separate entities. So I'm going to go ahead and redraw them where this is SDI, and then here is LDI. What is it that I already know? I already know right here that this angle, S, links with L, and then this angle right here, that's this angle right here. So I think highlighting it, splitting it apart is a good strategy. So that angle is that angle. For this triangle right here, that angle right here goes right there. So right now I have two pairs of corresponding angles that are congruent. So linking up that third angle is not going to help me here. I need some sides. So when I look at what sides I could link up, I remember, oh, common side. This side right here is a common side for both triangles. So I can use the reflexive property to link it up here and here. So here we're seeing, again, reflexive property of congruence. So if I name this first triangle SDI, the second one would be LID. I have two angles and a non-included side. So this would be angle, angle, side. All right, I'm going to flip it over. We're going to do some proofs on the back. All right, so here our goal is to prove the triangle's congruent using one of these 5 options. So here we're starting with 2 givens, and we want to see how those build. This is going to be a day where I start to split them up. So if I look at my first given, my given is that BA runs parallel to RK. So I only mark it as I write it, so I make sure that I can see how I'm connecting the dots. All right, so I'm starting with parallels. I don't know which of these 5 it's going to be yet until I start marking my diagram. All right, so I have the parallels. Okay, I have a transversal then. And then I can see that, oh, I have these alternate interior angles here and here. So now in 2, I can say that angle ABR so ABR will be congruent to KRB. Alternate interior angles theorem. Okay, so I built my first layer off of the parallels, but now I'm kind of stuck. So I look at my next given, and I see that K is congruent to A. Given. And as I write it, I mark my picture. Okay, so I have 2 pairs of corresponding angles. I know I'm going to need a side, and I see, ooh, I got the reflexive property. I have that common side. So right there, single tick mark. So here I can say that BR is congruent to. Okay, so if I name it BR, let's say that I look at that top triangle, B to R. I'm naming it from the single tick mark to the unmarked angle right here. So if I say B to R, for this one on the left, that's R to B. The order flips. And my reason is the reflexive property of congruence. Okay, one other place I can see that my order would flip is if I go back to my congruent statement. See how for one triangle, BRK, so if I follow that order, B to R, over here it's R to B. So my statement also shows me how my corresponding parts link up. Look, the K, the angle K, links up to where the A is right here. I know that those are congruent. Okay, so just pointing that out to you too. All right, so now what is it that I have? I have 2 angles and a non-included side. So this is angle, side, angle. I can reach my conclusion that BRK is congruent to RBA. Angle, angle, side. All right, next one. So here I'm given that BI is the perpendicular bisector of NR, and I also know that NI is congruent to RB. So again, I'm going to start with that first given and see what I can build off of it. So BI is the perpendicular bisector of NR, given. All right, so what does that mean to be a perpendicular bisector? So we're saying that BI, this segment, is the perpendicular bisector of this segment. Well, the first thing that I probably take from it is that if I see perpendicular, that creates right angles. So I can say that angle BAR is right. And I can also say that IAN is right. That's what it means to be perpendicular. It creates these right angles. So here I'm citing the definition of perpendicular. Okay, and now step 3. Okay, these angles are both right angles. I don't know if I'm using HL yet or if I'm using something else. So I want to tether those angles together and say, well, if they're right, they're congruent. So I'm going to say that BAR, that angle, is congruent to IAN. Okay, and that's just the definition of right. Right angles are congruent. They're both 90 degrees. So I usually write this as definition of right, but I could also write a statement that just says, well, right angles are congruent. All right, one other thing that I'm taking from this language, right, perpendicular bisector, is that language of bisect. So if I know that BI is bisecting NR, it's splitting it into two congruent parts. So I can say in step 4 that NA is congruent to RA. So NA, RA, right? That's what it means to bisect. So I'm going to say definition of bisect. If you said bisector, that's fine. I'm just going to say definition of bisect. All right, so all of that was building off of that language right here of perpendicular bisector. And now I'm stuck. So now I'm going to look at my other given, where NI is congruent to RB. Okay, so if I mark that now, NI and RB, double tick mark, that was given to me. Now I see that this is HL. They are right triangles. I do have two congruent legs and two congruent hypotenuses. So I can reach my conclusion right now. I can say that triangle BAR is congruent to IAN because of HL. Hypotenuse leg. All right, I have two more. Let me slide up. All right, looking at C. So C, I'm giving you two sets of parallels, so I'm going to build off of each one. So my first one is saying that ST is parallel to PA, given. So ST to PA. So there we go. It's the little arrows. Okay, let me emphasize those, just like that. Okay, and let's say that I view this as my transversal, right there. So then I see, okay, I can build off that. I see some corresponding angles right here and here. You can see that that angle would slide into that position perfectly. So I could say that angle STA is congruent to PAM, corresponding angles postulate. Okay, now I'm at a dead end, so I'm going to pick up another given. So I'm also told that SA, right here, runs parallel to PM, right there. So let me mark that in a different color. I'll make that purple. So now here at 3, step 3, I'm going to say that given SA runs parallel with PM, given. And then if I build off of that, right, then I have another pair of corresponding angles here and here. So I can mark that with a double tick mark. And I can say that angle SAT is congruent to PMA. Corresponding angles postulate. All right, so now I'm at another dead end. So I pick up my last given, which is right here. So point A is the midpoint. Just label that. Midpoint of TM. So A is the midpoint of this segment. So that midpoint then will split this segment into two congruent parts. I see exactly where I'm going to head. Let me just state that given next. So point A is the midpoint of TM given which if that's a midpoint, it splits this segment into two congruent parts. So I can say next that TA is congruent to AM. Definition of midpoint. Okay, and now I have my conclusion. I can reach my conclusion. So I know that STA is congruent to PAM. I have angle, side, angle. All right, last one right here. So here I am again. I'm given two things, and I want to build off of each one. So I'm going to start with that first given, that angle 1 is congruent to 2. And then I mark my picture as I go. So these angles, they are congruent. Okay, they're on the outside of my triangle. I'm trying to connect these two triangles. So I have to think of, well, what can I use then? Well, I can see that these form a linear pair, so do these, so they have to be supplementary. And if these angles are supplementary, these two, then these angles would be congruent. They are congruent supplements. So remember that supplements of congruent angles are also congruent. So I just have to make that connection. So in step 2, I need to say that angle 1 and 3 are supplementary angles. I'm going to keep it abbreviated. And then same with 4 and 2. Right? We know that that's because they form a linear pair. Linear pairs are always supplementary, so I'm citing the linear pair property. All right, so if I know that these are supplementary, same with these, then I know that 3 and 4, they have to be congruent, right? Because they are congruent supplements. So here I can say that 3 is congruent to 4. Congruent supplements theorem. Okay, so then next, I'm kind of at a dead end, so now I want to look at what else I'm told. I'm told that TM bisects SE. Okay, so I'll throw that in here, and then I'll stare at my picture and see if I can make another connection. So TM bisects SE. Given. Okay, so if TM bisects SE, then these segments here and here must be congruent. So I can say that SM is congruent to EM, definition of bisect. Okay, so now I have one pair of angles and one pair of sides. I'm really used to doing the reflexive part, but that's not going to help me here, right? That's not going to help me here because that would give me SSA. So I really can't use that. So I have to look for something else. And one thing that I can see is that this triangle right here, it has to be isosceles because I have base angles that are congruent. So I'm going to try that. So triangle TSE is isosceles. If a triangle has two congruent angles, right? Those are the base angles, then it is isosceles. Okay, and then what does it mean to be isosceles? It means that we have two congruent sides. Those are the legs. So once I've called it isosceles, then I can link up here and here. So TS is congruent to TE. So if the triangle is isosceles, then it has two congruent sides. And now I have enough. I have side, angle, side. I can say that my two triangles are congruent. So right here, step 8, I can say that triangle STM is congruent to triangle ETM. Side, angle, side. Okay, and as we get deeper into proofs, I just want to remind you that there are alternate pathways. You don't have to link things up in my exact sequence. I'm just trying to model for all of you the most efficient pathway through a lot of these proofs. And you will always have that resource with all the language available anytime that we assess with proofs. All right, have a good rest of your day.